Welcome back to the Bioprocess TEA calculator. If you have not watched the overview videos, I would do that now. In this video, we will cover the basics of how the calculator models the fermentation. The fermentation starts with the microbe, which by default is modeled to be a bacterial cell such as E. coli. The advanced settings enable users to alter key parameters and effectively model any microbial cell. The cells consume feedstocks, currently modeled as glucose, the source of carbon and reducing equivalents, ammonia, the nitrogen source, and oxygen. Cells are able to convert the building blocks to either more cells, i.e. biomass, or to the target chemical product, according to the appropriate conversion reaction. Byproducts are limited to carbon dioxide and water, which are generated from the complete oxidation of glucose. The model currently produces byproducts due to inefficiencies in growth. The default assumes that only 80% of the theoretical conversion of feedstocks to biomass is achieved, with a 20% loss to byproducts. This fraction can be changed in the advanced settings. With this fundamental framework, the calculator starts with the user input titer to define the amount of chemical made, and then with the user set yield defines the amount of biomass and sugar used, and next with the user input rate determines the fermentation time, after which a logistic model can be built for biomass growth and product formation. The chemical is produced according to the conversion chemistry, and the target final titer is used to calculate the final quantity or mass of the chemical made. Next, the yield is used to calculate the total sugar that is consumed and converted to the target chemical. The sugar not used for chemical production is the amount left over, if you will, for biomass and byproduct synthesis. This is one reason the maximum yield is limited to less than 100%, because some level of biomass is needed for the fermentation to proceed. The higher the yield, the less biomass can be produced, and the more productive the remaining biomass needs to be per cell to produce the chemical and achieve the target titers and rates. Incorporating the average rate of production, we can finally calculate the overall time of the fermentation and from this fit a logistic growth and production model. This model assumes growth-associated production, or in other words, a set amount of product is made per amount of biomass that is synthesized. This covers the basics of the fermentation model. Check out the other tutorials, and as always, thanks for watching.